Hello, this is Ivy Epstein here, looking over the beautiful city of Caltech. Now, to commemorate this beautiful view, we're going to look at some potential functions. The beavers here love to look at, calculus and integrals and stuff, so we're going to make like them and learn how to make potential functions and how they might help us in evaluating line integrals. Let us begin. So, usually when we want to evaluate a line integral, we evaluate f.dr. However, this is usually pretty hard because we have to plug in the parameterization of our function to the force and then dot it with the derivative of this parameterization. Hard, tedious, boring. Let's see if there's a better way. So let's apply the fundamental theorem of calculus. If we have a function such that the derivative of that function is our gradient function that we're plugging in, we can simply take that function and evaluate it at our 2 points, a and b. F of b minus f of a will give us our fundamental thing. So, if we can find a potential function such that the derivative of that function is our force field that we're trying to evaluate over, then we're good. We can just plug in and it's easy. First of all, let's consider the cases where this is possible. For our equation to work, we need the potential function f, which we're solving for the partial with respect to x to be the x component of our force field, and the partial with respect to y to be the y component of our force. If this is not the case, then obviously there is not a potential function. There's a more analytic way to solve for this, which you take the second derivative matrix and make sure it's symmetric. But we'll get to that once we instill some intuition about what we're doing here. First, let's consider a simple example. F of xy equals 2x plus 4y 4x plus 3y. So, what we can do is take the integral with respect to x here and with respect to y here. If we do such a thing, we get the integral 2x plus 4y dx. Here we are treating y as a constant because we are integrating with respect to x. When we carry out this integral, we get x squared plus 4xy plus c. See, usually in integrations, this c is just some boring old constant, but here this is very important. We will keep this in mind. So now let's take the integral with respect to y. Integral of the second component, 4x plus 3y dy. Evaluate that, we get 4xy plus 3 over 2y squared plus c. And please note that these are different c's. So, what we notice here is that we can combine these two using this c and this c. For this to work, if c equals 3 over 2y squared, and here c equals x squared, because those are both constants with respect to the other variable, we can plug it in and get an ultimate function, x squared plus 4xy plus 3 over 2y squared. So, if you think about that function, if you take the derivatives with respect to x and respect to y, we should get our original function. So let's scope that, see what's going down here. So, the derivative with respect to x is simply 2x plus 4y, because this is a constant with respect to x, and the y is a constant, so we just get that. With respect to y, little 2 comes down, we get 3y plus 4x, and that is actually originally what we started with. So it's kind of neat. All you have to do is take the integral and use the constant of integration as your chiller. So, with the equation we just worked out, we can analytically prove in general cases that when is a case we can find a potential function. It intuitively makes sense that you need to be able to take the x component of our thing and integrate with respect to y, and the y would integrate with respect to x. So what we can do is take the second derivative, which is a 2 by 2 matrix, and see if it's symmetric, which means if you take the x derivative and then the y derivative, it should be equivalent to taking the y derivative and then the x derivative. So consider the function we just did. X squared plus 4y, y squared plus 3y. So, if we take the matrix of this, we get x squared, the matrix, the columns here represent x and y derivatives with respect to, and the rows represent the different equations we're plugging into. So, when we take the derivatives with respect to these, we get x squared, 4, and then 4, 3. If you look about this line, it is symmetric about this diagonal, which clearly demonstrates that the derivative with respect to x and then y is the same as the derivative with respect to y and then x. So this clearly shows that you can actually find a potential function. It exists. Now let's try a harder example. So if you look at this function, it looks pretty gross. So, however, that's not an issue because if we apply our methodology, it'll be beautiful. So, if we take the integral with respect to x of this is simply just a constant, so we can treat it like that. If we remember some trigonometry and some calculus, we remember that this is simply, the integral of this is simply arctan. So, we get the integral of x over 1 plus x squared dx plus the integral of arctan y dx. So this is simply just arctan x plus arctan y times x, because this is simply just a constant, plus c, my friends. And interestingly enough, we notice that if we take the derivative of this with respect to y, this homie is just a constant, because there's no y's in there, so it goes away, 0. This homie, there's an x times this. So the x is just going to be a constant, which is why we see an x appear in the numerator. So we just take the arctan of y, which by symmetry we see is right there. So simple methodologies like this imply that all you have to do is take the derivative and see if it works. See, most people would say you have to do the thing we talked about, taking the second derivative, making a 2x2 matrix. But I really don't like that way because it's a lot of extra work, and you can simply just analytically prove or not that a potential function exists. If you can find one, you know it exists. And this kind of simple way does that. So simply just take the integral with respect to x, see what happens when you take the derivative with respect to y. That's all you need to do. And then, once you have your potential function f, solve for here or wherever you are, all you have to do is fb minus f of a, where b is your endpoint and a is your beginning point. Because, like we said, that's all you have to do for the fundamental theorem of calculus. Easy stuff.